In our last session, we introduced the idea of solving nonlinear equations, and we ran across a few issues. In particular, we realized there could be multiple solutions. In order to come up with a systematic approach to solving them, we made a minor adjustment to our nonlinear equation by just subtracting both from the left and the right of the equation whatever it took to create a function that was set to 0. And this allowed us to use root finding as our method of determining solutions to nonlinear equations. So now we're going to introduce our first method of doing so, called the bisection method. When we get into it, it will appear a lot like that military procedure of shooting a projectile too far once and too short a second time in order to find out where the happy middle ground is, if that might be happy. And we're going to be doing something much like that here. Let's go back to that fairly simple quadratic we introduced last time that we're looking at in front of us, and it had two known solutions that we were able to analytically come up with. Now, of course, in general, we will be having nonlinear equations that we can't get the analytic solution, but it's good to test our system on something for which we know the answer. So there's a picture of that quadratic. Graphing the function first is always a good first step because you can visualize how many roots there are and where they're located. But before we solve this problem, let's just make a comment about it, and that is we might have been a little lucky we had any roots at all. If we had added a big enough constant to this function, the entire parabola would have lifted above the x-axis and there would have been no roots at all. We could have had our algorithm chasing after something that didn't exist, and it might run forever trying. So that's another really good reason to graph it first. We also might have added a constant just enough so that the raised parabola just kissed the x-axis, in which case there would be one root and not two, but we would also have a problem with this bisection method for reasons that you'll understand in a minute. So again, looking at it is important before you start throwing algorithms that may or may not work. So let's take our quadratic and see if we can't apply the method to one of these two roots. And I am going to focus on the left one. I need to find, as a first step, two points that straddle that root. I need to find one that I'm sure is on the left of it and one that I'm sure is on the right. So I am going to pick x equal to 0.3 and x equal to 0.6 as my candidate starting points for this bisection method. Well, if I evaluate f of 0.3, we get a number that's clearly positive, and if I evaluate f of 0.6, I am going to get a value that's clearly negative. That is the requirement for starting this game, and throughout this algorithm, we're going to have to maintain that structure. Now what we're interested in doing is constructing a point halfway between our initial guesses and determine where that point lies with respect to the x-axis. Since we determined that these 2 points are straddling the x-axis, let's just draw where they are. So 0.3, our initial left guess, is clearly here. Our right guess is clearly at the bottom. And I now have an interval over which my solution must exist. The game here will be to cut this interval in half and come up with a new value, which will be 0.45, and test to see if the functional evaluation is positive or negative. If it's positive, then we want to replace the previous leftmost one with a new one. If, on the other hand, this were to be negative, we would want to replace the right value. So clearly this is going to be positive, which means we eliminated the left value and cut our interval in half that straddles that trapped root. Now we just repeat the process. We have a left value of 0.45. We still have a right value of 0.6. We average the two together again. We're going to get a 0.525. And once we get that, we will need to determine whether it's positive or negative. And visually at this point, we can see it must be negative. So let's just do that. And that means we would need to replace the rightmost point with this new value that still produces a pair that straddles the root. Okay, so let's do it one more time just to illustrate the point. If we average these two values, it's pretty obvious that the average value will still be above the line, so we'll replace the leftmost value. And we continue to cut this interval in half and half again and half again until we get close enough. Well, what does close enough mean? We're going to look at that in a little bit because there's more than one way to determine if you're ready to quit. But let's go ahead first and look at a potential algorithm that will accomplish that bisecting approach. So step one is to determine an engineering tolerance. So this is the limit of error that we're going to tolerate in the result. We also need to put in our initial guess value on the low side and the high side. In this case, it was 0.3 and 0.6. I'll explain this next variable later, but I'm going to set what I'm calling x previous to a very large value, which I'm calling infinity. And I want to start a counter variable to be 0. Now I'm ready to start my looping process that will continually cut the interval between the high and low guesses in half repeatedly. I'm using what I'm calling a repeat until loop that is kind of like your for loop or your while loop in the sense that the code trapped in the middle is repeated until some criteria is established. You're not going to find this repeat and until loop in MATLAB. You won't even find it in C++. You will find it in a programming language called Delphi, but we will use that as valid pseudocode for explaining this algorithm. What a repeat and until structure is doing is it guarantees entry into a loop with no checking whatsoever. After it accomplishes all the code, it evaluates a criteria to see if a stopping condition has occurred. If it has, then you just continue to go out. If it hasn't, you loop back up to the beginning of the repeat loop. If you wanted to change this to be a while loop, you simply change this command to while. You would take the opposite of this criteria and put it with your while statement and then put an end down here. So the two loops do the same thing. It's just whether you want to check at the top or at the bottom. Now let's suppose we are on our first pass through and we enter into this code and we need to construct the middle value between our low and our high. Well, that's just the average. So we'll take the average, store it in a new variable called xmid, and then we will use xmid, evaluate the function at that point, and store the result in something called ymid. We now need to determine if ymid is above 0 or below 0. If it's above 0, we want to replace the left-hand side. If it's below 0, then the higher value of x needs to be replaced. So we set up an if statement. If ymid is positive, we'll take this newly constructed middle value and clobber the low value. If that isn't true, in other words, if ymid is less than or equal to 0, then we'll do the opposite. We'll take this xmid and clobber the high value. In either case, we want to come up with some kind of error that will be comparable to our engineering tolerance. And what we're using here is something called a relative error. We're looking how far our middle value is from the previously calculated value on the previous loop. Well, we don't have a previous loop, but we do have a x previous that we've set arbitrarily to be a large number. So this difference is going to be huge. We'll take that difference and divide it by the midpoint to compare the error with the actual value. So this is a relative error that we're interested in. We're now going to preserve this midpoint in this x previous variable, increment the loop, test to see if our criteria has passed or not, which it hasn't in this case because our error would be so huge, and then go back to the beginning and try the loop again to see if we can make the result more accurate. So we just do the same thing. You take the newly formed x low, add it to the x high, take its average, we just cut the interval in half, and we have a midpoint. Evaluate that midpoint, use the function, and we store that in y midpoint. And then do the same thing. Is that point above the axis, below the axis? And clobber either x low or x high, depending on whether y mid was positive or negative. So now the error term makes more sense. We can compare this new middle value with the previous middle value. And this difference gives us the width of the next interval. If we take that as error and divide that by the middle value, our new estimate of the result, then we get our relative error. We preserve the result of the midpoint, increment the run, and ask if that error is small enough. And if that error is small enough, we quit. If not, we just keep going around and around and around until we do. So this algorithm is now complete. It has some risk in it, however, in that the looping process could go on forever if I've made some logical mistake in my code. So it would be a lot better to at least initially test for this n value within this criteria. So maybe put a parenthesis around the criteria that's there and put or n is bigger than 50 or 100 or something fairly large, but not so large that this thing never comes back if you make a mistake. So this code's a little dangerous, and you would be better off by adding a safety switch just in case you make a mistake in your algorithm. Okay, so we've really got a nice method now to use this bisection code. You'll get a chance to try this in homework in a little bit, but before we do that, I'd like to introduce a few more concepts, and one is the stopping criteria. There's a second stopping criteria that might be just as good and possibly better as the one I used. If I start the algorithm off exactly like I did before, but leave out this x previous variable, and if I do the same criteria that I had before and the same incrementing, what I could do is just check to see if the y value is sufficiently close to 0, epsilon being our criteria. Really, that's not bad. We're really asking, did it do its job, as opposed to how close did the interval get to be? And that might be a better criteria depending on the problem that you're trying to solve. So that's another way to go, a little bit simpler. So we've now completed the logic of our bisection method. And so we'll go ahead and pause here before we get into section 3.1b. But as we get into 1b, we're going to find that there are some problems or maybe some efficiencies that we could gain by looking at that method just a little bit closer. And we'll start next time realizing that we created an algorithm that only works if your function's going downhill. You might think about that for a minute. What would happen to that code if your function was going uphill instead of downhill? Would it actually work? And the answer is no, it would have problems. But there's a fairly minor fix we can make that we will introduce next time.